Okay, hi everybody. So we are back with the workshops. We have been like 3 months off. It's been a lot of work, so we are getting back on the horse and trying to do something different. Right now, we were focusing on LLMs and generative models for text. This is going to be something new for me because I haven't been so familiar with image generation, and during this workshop I did that. I deep into what are diffusion models, and that's what I'm going to try to explain here. We are going to skip on all the math because it's super complicated, but if you like that, you can get into the links I leave on the notebook, and there you have a really good explanation on how it really works, like seeing all the math behind the scenes. And believe it or not, it's super interesting. All this notebook is based in the work of other people. I put it there in the links, basically because this code is something like inventing the wheel again, so it makes no sense to repeat it. But we're going to go through some parts, and I will try to explain some of the parts and how the models work. Okay, so let's dive into what are diffusion models. Diffusion models, probably most of you associated with image generations because of the name and stable diffusion. That is, oh, sorry, I'm going to start running the cells here, like installing. Okay, so stable diffusion is one of the models for generating images that is open source and is one of the best. If you want another more generated image, it's like Midjourney or ideogram.ai. There are a lot of models that uses these diffusion models, right? Mm, First, let's see and go backwards. Let's go into go from the left, the beginning, the end. That is seeing the diffusion model that is in Hugging Face. You can run it like this, and we are going to see what the results are, and then we are going to go through the inner parts of that model. Not exactly that model, but all the other diffusion models. Right now, what I'm doing is loading Stable Diffusion from Hugging Face, but also loading Dreambooth. Dreambooth is a process for training Stable Diffusion with a set of images. Somebody did this and trained the Mr. Potato Head toy in Stable Diffusion and leave it here in Hugging Face. There are a lot of pre-trained models, so you can check there here and have fun. And just by using this prompt, I'm going to run it like an actual old painting of Mr. Potato Head riding a toy horse by Picasso. Let's see what we get. Right now we are running on Colab using GPUs. If you want to run this locally, you will need a GPU. I don't know what the horse is, but it's kind of a painting. So you can see that here with just a simple prompt, we are getting an image. Probably most of you have seen this because it's fairly common right now generating images from prompts. But how does it work? What is inside here? This is what I'm trying to explain. A diffusion model works in like training a network, a deep learning network, that what would try to do is not generate an image, but to predict the noise in an image. So let's see here in this graph, when you train the diffusion model, it makes a forward pass. Like you have a set of images and you say, okay, I'm going to like make 100 images for each one with different amount of noise. This noise is Gaussian noise that is a noise that is generated by a normal distribution. So that's why it's used, because we know exactly if we decide we're going to put 100 times, we know exactly for each time the amount of noise that equivalent for that Gaussian noise. So you will have an image, and let's say 100 part of that image with different amount of noise. From the pure image here, you can see that it's a phase without noise, to complete noise, where you can make anything from here. And what you do while training is showing the model, let's say in the like 10 amount of noise, you will see this image with this noise on top. So the model, we're trying to learn how much noise is in the 10 position, or the 20 position, or the 30 position. So it will try to know and predict that noise. We are not trying to predict how an image. We are trying to predict the noise inside on top of that image, right? So when you have that model trained, you will have a model where you put some image with noise, and the output is going to be a noise, an image of the exact same size and format, but only noise. So if you subtract that noise from your input image, you are going to get the original image. That is what's supposed to be. It's not so simple. You don't subtract the whole noise, because that would make it difficult for the model to predict. You're going to make it in steps. So you train the network. In this case, you're going to train a neural network. Oh, okay, sorry. You're going to train a neural network with this shape. It's called a U shape. And this is a fairly old network that we've used to classify images. But in the stable paper, they use this network because what it does is it starts scaling the image down to a simple, really like losing a lot of information, and they scale up. And while doing this, you're going to have the possibility to put these embeddings. Then the embeddings, while downscaling and upscaling, are going to have the information that you want to add to that image, right? So in this case, we are going to add the time. The time is like the position of the amount of noise. So if you have like at user side, you're going to have like 100 positions of noise. Each one is going to be a time, and that time is going to be embedded. Like the embedding of words, it's going to be a vector of numbers. And also you can add the context, like those words of those sentences you want to generate, like we did above here, like with Mr. Potato. This is going to be embedded and added here on the layers while upscaling and downscaling, right? So here in this image, we can see that in the training set, we had an avocado image, right? And a tag. That the tag is the text that is going to be embedded. And while we're training, we're going to say, okay, this noise over this image plus this embedding is a ripe avocado with nose. So the the embedding is going to be the words plus the time plus the image embedding. So from there, the model is going to try to learn, as with embeddings, the position and information that it needs to embed that information, right? So if you have an image with ripe avocado and a chair, when you do like this prompt, avocado armchair, this is going to get an embedding that is between both of them, because it gets the information from this, and it's going to put that embedding in the network, and that is going to try to predict the noise to get something near what is an avocado armchair, right? So as you see here, the magic happens with embeddings, as always. I'm going to go like rush through all this code because it's a lot of, but we're going to stop here. Here. This UNet is basically the network that we are going to use to train the model, right? We have this network, and this network has different parts. We have downscaling and embedding and attention and all different parts, and upscaling also. So these different parts are all this code that we are going to skip right now because it's a lot, but you can check it out later in the network, in the notebook. And we are going to go a little bit over the network, right? So you can see here that we're going to have first the embeddings. If you have a time embeddings, we are going to use it. And here it does the embedding, all the embedding using another function that is going to embed the position on the time that is going to make the image just being like in the decoding or the encoding. And the different layers. Here we got some downwards, like when we are going down in the layers, and then we are going upwards in the layers when we try to decode it. And finally, we are going to get a, an image, but it's not an image. It's just the noise that the model predicts that it's inside, that is on top of that image, right? Okay, let's run this. Okay, now we have all the code loaded in memory, and we are going to try to train a simple model using this stable diffusion. First, I'm going to download the dataset that probably most of you that have some machine learning experience probably knows, because it's fairly common. It's a dataset of numbers, handwriting numbers, that is used to predict. Let me show you this. These are the numbers. I'm going to run this. While we run, there are a lot of images of handwritten numbers, right? And as you can see, these are numbers. And what we are going to train is a model that it's not trying to create numbers. It's just trying to create things similar to this. So it's probably trying to create, it's going to try to create images of something similar to a number or to a letter or something handwritten, right? Let's do here. I'm going to start training the model because it's going to take some time while I explain other things. Here it is. It started training. So all this that I'm doing here is all in written using Torch, right? Basically, we are running a torch model, and we are training that torch model that is generated by this network that is a U network, right? So while we are training, what is trying to do is trying to predict how much noise is on top of every one of the images on the training set. So we have all the images of the numbers. This is going to add noise in the forward part of the training. It's going to add different amounts of noise. And since I have how much noise I have the original images, I can predict and compare that prediction and use a loss function to maximize that, minimize that, and get the best result of the model, right? That is what it's doing right here. The model is trying to do that. It's different passes and optimizing the model using Torch. Basically, you have a Torch model here where you create an optimizer. You run the different seeds, you add the different batches of images with the different noises, and that optimizer is going to, once it goes through an epoch here, I'm going to run 5 epochs because if not, it's going to be too long. Once it does that, it's going to modify the weights of the model and run it again a couple of times. And each time it's going to try to get better, right? This is going to take some time. While we do this, I don't know if there are any questions, but if there are, I'm going to try to answer later. Okay, let me. So while training here, we can go up again and try to get a little more clearance on how these models work. Let's go again to the graph. Okay, here. Let's go a little bit deeper on the network. So here you have an image, right? This image is one. It depends if you are training or if you are trying to predict. Let's say I'm trying to predict. How can I create an image from, like, let's say this? Let's use this example. I want to generate an avocado art chain. What is the model going to do? The model is going to have like a seed that is going to be an image of the size you want to create, just noise with full noise, like in the most position of noise, right? And what it's going to do with that is going to downscale that so it can focus the information. And in each part is going to add the context that is going to be the time of the position of the oh sorry, the position of the amount of noise it has, right? And the text that is added to the embeddings. And in each part, after it does that, it's going to go through the whole network. Once it gets the prediction, it's going to upscale that. And after every upscale, it's going to generate an image of the same size of the input, but only with noise. It's going to predict the noise, right? After that, what it's going to do is, instead of removing the noise, or it's going to remove the noise from the image, but instead of finalizing there, it's going to add again a little bit less noise than the original have. So I have an image with, like, say, let's say full noise. I'm going to remove that full noise and then add more noise, but not full noise, like 90% of noise, or let's say 80%. And it's going to do that a lot of times. It's going to loop over there. And each time it passes, it's going to remove a little bit of more of noise till the last time that is going to get, like, it's going to say, okay, now I'm in the position of zero noise. And that finally is going to be the output. So when you get there, after all the loops, you're going to get an image. Let's say this case. This is going to start from full noise, it's going to go through the network, it's going to predict the noise, it's going to remove that noise, and then again and again and again, a lot of times, till the final result is this. It's going to have a little bit of noise, but it's going to have pixels that are going to be predicted, right? And those pixels are going to be coming from the context and the different images that it has on training, right? The magic here is that it's kind of hard to get the grasp of how these images are being created. Basically, here you are removing noise, but while removing noise, you're defining pixels. So this pixel came from this image with full noise, and when you remove, it just said, okay, here is a green pixel. It's not noise, it's going to remain there. And that is how the images are generated. Let's see how is the model training. Okay. What's the question? Okay, let's see. Yeah, let me read. Are there ways to run this trainer black box, or do we always need to write all this code? Okay, yes, there are. We don't have to write. This code is basically to understand what's going on inside of the model. There are a lot of libraries here. I'm going to share it later. But basically, you get one where you say, I want to train a UNet, and you add some parameters, and you add the image data sets, and you get the trained model. Also, you have pre-trained models. As I showed you at the beginning, let's go back all this way. Here, what we are doing is loading a pre-trained model from Hugging Face. One with dreamballs from Mr. Potato Head, but there are a lot of other dreamballs, and also you can load like a vanilla version, just the stable diffusion. So in like 3 lines of code, you load the model, and after you load the model, you just have to send here a prompt and some parameters. Is you can change this and see how it works. But basically, in 4 lines, you can generate the image using stable diffusion. The problem here is that you need GPUs. That's the only caveat, because if not, it's not going to work. Right now in Leniolabs, I have 3 GPUs, but if you have like a fairly good graphic card, you will probably you could run this in your own computer, because the great, or the one of the most important things in stable diffusion is that most of the calculation and most of this like adding and noise and removing noise is being done here after the image is embedded. So you are not working with like the full image. Like imagine we have like 572 pixels by 572 pixels. You do the multiplication, you're going to have a lot of information. Stable diffusion, what it does is all the calculation, all the modifications are being done here in the middle, where after removing a lot of information, the image is embedded. So you are doing all the calculation on those vectors, and then is the after that, and before start the upscaling, that the image is being decoded from those embedded. So that's why stable diffusion is better to run in a fairly simple computer, because it doesn't need so much calculation power. Let's go to the model again. Here we go. We went through all the epochs that I put just 5 epochs, because if not, it's going to take a lot of time. But if you want to train a good model, you will need a lot of images from the data set, and you will have to run more epochs, because if not, it's not going to be so good predicting, right? In this case, what this graph just showing the loss function, it started here, and really fast it went super down. Yeah. This is because the data set is super simple with the numbers. Right now, what I'm going to do is generate a sample with that model. I'm going to generate 64 images, and now I'm going to see the images that are generated. As you can see here, the generated images are not near similar to a number. Here we have kind of an 8, but none of them are really a number. What's going on here? First, we are not training a model to generate numbers. We are training a model to generate images that might be similar to the original ones, in this case, these numbers. But if you have like one more like line here, it's not going to be a number, but it's going to be a similar image. So the model is trying to do that. It's removing noise from a lot of noise and trying to remain images that are similar to this. It's doing a good job. You can say that it's trying, and it's like doing lines on a black background. So it's kind of doing something, but it's not good. That's maybe also because the training was fast, because we don't have time. Right now, what I'm going to show is for one of these images, let's say this, all the stages, or no, we are not going to show all the stages because there are 200, but we're going to show 25 stages of removing noise. This is a starting point. This is all noise, Gaussian noise, sorry. That is just pure noise. After each one of these steps, what it's doing is removing a bit of noise and then adding again noise. And all this, you can see here that uh, after like this one, each one of these is like, I don't remember the number that I put, is eight, eight positions in the timeline. So after 540, 52 positions, you can start seeing like the image that is starting to be generated. And after that, you keep the model keeps removing noise, noise, and noise, and noise, and you get finally this last image. This is perfect. No, of course not. It's not perfect, but it's trying to do the job that we told him. Let's see another image. As you can see, the process is the same. Each image is going to have like starting point that is going to be the same, a normal distribution of noise, and after each pass of the network is going to remove a bit more of noise, and we finally get the predicted image. Remember, these diffusion models do not create images. What it does are remove noise. They are predicting the noise that is on top of the image. On the first pass after this noise, the prediction is going to be, if you remove all that noise, it's supposed to be this. But if you do that, you're not going to get this clear image. You're going to have a super foggy image. That's why it has to do more than once. It's got to do a lot of steps to remove a bit of noise in each pass. I don't know if there are any other questions. These models, let's see, let's go up again. Sorry. Okay, let's wait here. In this case, as you saw, I didn't have any prompt. It just uses it uses the time embedding. This part, the time, that's the epochs of the, not the epochs, sorry, the epochs are for the training. These are all the scheduled noise in the distribution of the training, right? So when I say that in each part it removes a bit of noise, I'm saying when the model, when they start here, it enters the full noise, and also it's entering the embedding for the, let's say, position 200. That's the one that you hear, that is saying you are in the 200 position of time of adding noise. So both of those things are I entering the layer, the network, and when I get out of here, I'm going to have the noise for the 200 position. On the second pass of this network, what is going to enter is the image with that noise removed, the noise generated, but I'm going to add the noise for the, let's say, 80 position. And that's going to go again and again and again till we get to the position zero, where we get the noise. That's the last step to remove to get the image. Yeah, another question. So the other yes, in this case, I put 200 because just a test. But I think that for the paper where this is coming from, they use like 1,000 steps. It's not like every time it goes through all the steps. What it does is like when you have, let's see if we have an image here. If you go here, you see xt. This t is the times, right? So in this case, in the training, while I was training here, I put the t in 200. As it says here, when they train in the model where the stable model came out, they use 1,000, right? So what this means is that I have an image, and if I put this image to the training set, I can put 1,000 times different amount of noise increasingly to get to the full noise, right? The good thing about this Gaussian noise is that it can be the noise is from a normal distribution and can be predicted without having to go through all the stages. So if I said I have the image, I know how many steps in the distribution I'm going to have, I can say I want the image with, let's say, step 200, and I'm just doing a math equation, and I get that. I don't have to go through all the steps. So during the training, I can show the model, that is the network that is training. I can show different stages. I don't have to throw all the stages for all the images. That would take a lot of time. I can just select a sample of for each image, different stages. So that's going to make the model train faster, and it's going to understand that for stage, let's say stage 100, the amount of noise that I need to remove is this amount. I hope that answered the question. And let's go a second, because it makes no sense to go through all the code, but basically, as I said, you can import, if you want to try the model, you can import in one line. This was just if you are more like trying to get into the magic behind. And I'm going to go through. This is what I base all this notebook. In this blog, they went through all through the paper, and what they did is explain all the math behind this. If you have time and you want to do it, you can do all this equation and write the functions. That's what is being done in the notebook, with some help, obviously, from different parts of Torch. But what is being done here is writing all that math functions here in the code and running them in the network. So all the work that is already done on the library, you have it here, so you can understand the different parts and how each part works. So you have the different math here. You can see here for the embedding of the time. You see that you do the logarithm, then you arrange with the torch. You take some parts and you do the embedding. All of that, you can see it here. This is all based on that other blog post that I found is super, super good to understand all the math. Well, that's it. I don't have anything else. I don't know if anyone has any other questions. We can go on. The magic of the diffusion model is that not only they work for images, but they also work for music or for I don't know, any other thing you can embed. You can do the embedding on anything, because you can convert whatever into a vector, a number. You can do a wave or whatever, and you change it into a number, and it goes through the same process, and you get a diffusion model for music or for sounds or if something like that. Okay, so I hope that, even though it's kind of difficult and we didn't go through all the details, you can take a look at all this code and maybe go to the sources and understand the math behind this, because if you want to have a clear view of how this works, it's super useful. Okay, no, we stay there. I don't know when it's going to be the next workshop, because we are running a bit late, but we'll probably try to have one in 2 weeks. I don't know the subject, but it's probably going to be on diffusion, but no trying to explain the math or the code that generates this, just doing different parts or trying to train a model with Dreambooth and trying to create images based on or another one, like in painting, or different techniques that you can do with different models of image generation. Okay, everybody, thanks for coming. I hope you have a good time and you understand a little bit more of this.